Hello everyone and welcome back to the channel. In today's video, we will be running official YOLO v7 instance segmentation. I will walk you through the process of setting up the environment, installing necessary libraries, and writing the code from scratch for instance segmentation on images, videos, and webcam. The code will be available for our Patreon supporters. Let's get started. First, let's install Microsoft C++ build tools on Windows. You do not need it on Linux. Once you run the setup, select desktop development with C++ and click on install. When installation is finished, restart the computer. Now open Anaconda prompt and create a virtual environment by command conda create -n YOLO v7_mask and Python is 3.9. Hit enter, press Y, hit enter again, and once the process is finished, activate the environment by command conda activate YOLO v7_mask, and here we have our environment. Now install Cython by command pip install Cython. Now we need to install PyTorch with GPU support. Go to official PyTorch website, click on previous PyTorch versions, and I like to install PyTorch 1.11 with CUDA 11.3. However, latest version have some error, which I will get into in a moment. If you want to avoid that, you can install PyTorch 1.9.1 with CUDA 11.1. But I will go with version 1.11. Just copy this pip command and paste it in Anaconda prompt or terminal if you are on Linux. If you also choose to install this latest version of PyTorch, we need to modify one file. Go to your C drive, then users, then your username, Anaconda 3, envs. Here you will find all the environments that you have created. Go to your YOLO v7_mask folder, then lib, site packages, torch, nn, modules, and open upsampling.py. Go to line number 154 and comment this recompute_scale_factor parameter. Make sure the closing bracket is after the comment. Save the file. There is a quicker way to find this file as well. I just use this small utility called everything, and if I search the file name here, upsampling.py, it's going to give me that file real quick, and I can just double click on it and modify the file directly from here. Now we go to Detectron2 official repository and copy this git link. You can install git for your operating system to use git clone command. I already have installed it on Windows, so I can issue command git clone and then paste this link. You will see a folder called Detectron2 in your local hard drive. Once it is cloned, go to official YOLO v7 repository and download it as a zip file. Extract the file, take these files out of the subfolder and delete the empty subfolder called YOLO v7-mask. Alright, now that we have these two repositories, on your Anaconda prompt, go to Detectron2 folder and issue command pip install e dot and hit enter. It will download and install required libraries and set up Detectron2. Once it is done without any errors, go to YOLO v7-mask repository via Anaconda prompt, and now we will install additional libraries. But before that, open requirements.txt from YOLO v7-mask repository and delete torch and torch vision from here, as we already have installed them. Save this file, then from Anaconda prompt, issue the command pip install -r requirements.txt. This will install the remaining libraries required to run instance segmentation using YOLO v7. The installation is now complete without any errors. Let's run Python and import Detectron2. It's imported without any errors. Then import torch and issue command torch.cuda.is_available. It says true, which means we can use GPU. Now go to official YOLO v7 repository and then click on releases, then on assets, and find YOLO v7-mask.pt. Here it is. Download it and save it in YOLO v7 repository that we have on our local machine. I already have downloaded this file, so I'm just going to paste it here along with 1.jpg and a video called ac_parkour.mp4. We will use these files for instance segmentation. Now we have everything set up and we are ready to code. Let's open detect.py from YOLO v7-mask repository. We will need piece of code from this file. Create a new empty file called segment.py. From detect.py, copy import argparse and paste it in the segment.py file. Now in detect.py, scroll all the way down and copy the code from if__main to the end and paste it in the segment.py. Now these are the arguments that we can use in our code, but we do not need all of them. So remove -- device, -- save txt, -- save -conf, -- classes, -- agnostic -nms, -- augment, -- update, -- exists -ok, and -no -trace. Now we need to make our own edits. The weights file is the one that we just downloaded, so let's just change it to YOLO v7-mask.pt. Also change the default value of source to 1.jpg. Rest of the things are fine, but we need to add a few more arguments. Let's copy this string argument definition and paste at the end here and change this to --hyp. This is the hyperparameter file for YOLO v7-mask. It is located inside data folder, this one. So just change this default value to data/hyp.scratch.mask.yml so that we do not need to define it again and again when running the code. Next one is the integer parameter. So just copy any existing integer argument and paste here. Let's call it seed and it will be used to change colors of the instances if we need. Let's set this to 1 by default. We need another integer argument called thickness. It is to control the size of the bounding boxes and the font. Let's also set it to 1. Now we need boolean parameters. So let's copy this one and paste at the end. Call it no bbox. And if this is set, bounding boxes around the instances would not be shown. Create another boolean argument and call it no label. If this is set, the label will not be shown on the instances. And finally, another boolean argument called show FPS. And if this is set, the FPS will be shown on the video or webcam stream. That's it for all the arguments. These arguments will be parsed and stored inside a variable called OPT, short for options. We will be using this variable a lot, so keep that in mind while coding along. Now let's fix NumPy random seed with whatever we have from our parsed arguments options. Then we need to check if CUDA available. If yes, we will use CUDA 0 as device. Otherwise, CPU will be used. And if we use GPU, we can utilize half precision. So let's define a flag which is set to true if device type is not CPU. Now let's load weights using opt.weights argument. And from weights, let's get the model and place it on the device, which is GPU in our case. And if half precision is possible, let's ask the model to use it. Now we open hyperparameter file with open opt.hyp as f and hyp equals yml.load f. Loader equals yml.fullloader. We have not imported any of the libraries yet. We will do that in a moment. And now if we have not set the -- no save argument, it means we want to save the output. So we need to define a save directory. Save_dir equals path, then increment path, then path opt.project/opt.name. exist_ok equals false. And then we create this directory, and if it already exists, we do not do anything. Save_dir .mkdir parents equals true, exist_ok equals true. The save path then would be this save directory and the source file name, because we want the output to have the same file name as the source. We also need to determine if we are using webcam. So if opt.source is numeric, it will set the flag webcam. And if the webcam is true and we have not set no save flag, we want to add .mp4 at the end of the save path, because it will be an integer representing the webcam number, so we need to add an extension to the output. For videos, the extension is already there in the source, so we do not need it. We also need to determine if the input is a video or image, so that we can call relevant methods later on. So we define a list of image formats. So we allow MBP, JPG, JPEG, PNG, TIFF, DNG, WEBP, and MPO. Similarly, for video formats, we allow MOV, AVI, MP4, MPG, M4V, WMV, MKV, and with torch.noGrade is fine. The rest of the code is not needed. Now, if we split the source file name based on dot and look at its last entry, it will give us the file extension. If it is present in img_formats list, we call a function on image. Else if this extension is in video format list, or if webcam flag is set, we call on video function, because webcam and video functions work identically. Otherwise, we print a message that it's not a valid source. Now our main function is complete. We need to import the library. So let's do that. Import time from pathlib, import path, import torch, import CV2, import YAML. From torch vision, import transforms, import numpy as np. And now we need to import utilities from YOLO v7-mask repository. So from utils.datasets, import letterbox. From utils.general, import non_max_suppression_mask_conf and increment_path. From detectron2.modeling.poolers, import ROI pooler. From detectron2.structures, import boxes. From detectron2.utils.memory, import retry_if_CUDA_OOM, which stands for out of memory. From detectron2.layers, import paste_masks_in_image. That's it. Let's save this file and run the code using Anaconda prompt just to be sure if everything works fine. There is an error. I have misspelled memory. Let's correct it and run the code again. Now everything works fine. Of course, it's calling on image function, which we have not defined yet. So let's define it right above this if__main statement. So image equals cv2.imread opt.source and assert image is not none. If it is none, let's print message that image is not found. If image is found and read, we need to change it from BGR to RGB, as CV2 reads images in BGR format, and we save the size of the image in a variable called img_size. Now we need another version of the image which will be used to show all the masks, labels and bounding boxes, which will be used to display, but we have not defined a function to get all the predictions for anything. So just make a copy of the original image for now and store it as image_display variable. We will replace it later with predictions. And now we resize image_display back to the original resolution that we just stored above. If no save option is not set, we want to save the image. So call cv2.imWrite and write the image on save path, and the image that we want to store is image_display. Then print the message that the output is stored at this particular path. Similarly, if opt.view_image is set, by the way, this hyphen in the arguments is parsed as underscores, so we will be using view_img here. So cv2.imShow in a window called results show image_display. Then we wait for a key press indefinitely. Let's run this piece of code and see if it works fine. Python segment.py --source 1.jpg. I have missed R in BGR to RGB. So let's type it in here and try again. Everything works and it says that the output is stored at this location. If we go there, the image is stored, but of course nothing is plotted as of yet. We can also test other flags, --no save, --view -img, and we can see this time it displays the result but does not save anything. Alright, now here instead of copying the original image, let's call a function called process frame and pass the image as a parameter. Now define this function which takes an image as input, and we will call letterbox function to resize the image to 640 by 640 resolution and get the resized image from index 0 of the function return. Let's save a copy of this resized image as image underscore for future use. Now convert image to tensor by calling transforms.toTensor on the image, and then image equals torch.tensor of np.array of list of image.numpy. Now we shift the image to the device that we detected, which is GPU in my case. And if we have half flag set, we convert image to half precision, otherwise to float. Now let's call the model and pass the image to it and save the output to output variable. The model produces the output dictionary with 6 things: information out, train out, attention, mask intersection over union, basis, and semantic output. Let's unpack these. inf_output would be output at test. Train underscore out is going to be output at bbox_and_cls. ATTN is going to be produced from output at ATTN. Mask_IOU is produced from output at mask_IOU. Let me maximize this window. Basis from output at basis, and sem_output from output at sem. Now we concatenate basis and sem_output tensors, and we also need the image size. So the number of batches, then channel, which we do not need, so just put underscore there, then height and width equals image.shape. We can also extract class names from model, so names equal model.names. Now we need to define the pooler. Pooler equals ROI pooler, output underscore size equals HYP, which is this YAML file that we loaded here. At mask underscore resolution, scales equals model.pooler underscore scale, sampling underscore ratio equals 1, pooler underscore type equals ROI alignment v2, canonical underscore level equals 2. Now we need to perform non-maxima suppression, which basically removes any overlapping bounding boxes. It's going to produce 5 things: output, output underscore mask. These two are the most important. Then output underscore mask underscore score. Then 2 more things. Let's call them output underscore AC and output underscore AB equals non underscore max underscore suppression underscore mask underscore conf. Let's pass inf underscore out, then ATTN, then basis, then pooler, HYP, conf underscore THRES equals opt.conf underscore THRES, and IOU underscore THRES equals opt.IOU underscore THRES. Merge equals false, mask underscore IOU equals none. Now we need to unpack the information that we need to plot on the images. So PRED and PRED underscore masks equals output at 0 and output underscore mask at 0. We also need base image, so base equals basis at index 0. Now we need to plot this information, but only if prediction is not none. So if PRED is not none, only then we want to execute this code here. So bboxes equals boxes from PRED, all rows and 4 columns. original underscore pred underscore masks equals pred underscore masks dot view -1. Then the resolution which can be obtained from HYP at mask underscore resolution and HYP at mask underscore resolution again. Then pred underscore masks equals retry underscore if underscore CUDA underscore OOM paste underscore masks underscore in underscore image original underscore pred underscore masks, then pass b boxes, then as a tuple height and width, then threshold equals 0.5. Now we need to detach everything from GPU tensors and convert it into CPU based arrays. So pred underscore masks underscore np equals pred underscore masks dot detach dot cpu dot numpy. Pred underscore cls, which is prediction class, pred all rows and fifth column dot detach dot cpu dot numpy, pred underscore conf, which is prediction confidence, pred at all rows fourth column dot detach dot cpu dot numpy, and number of bounding boxes equals b boxes dot tensor dot detach dot cpu dot numpy, and we want to convert it to integer, so dot as type integer. Now we need another variable image underscore display that is equals to image at 0 index dot permute 1, 2, 0, and we want to multiply it with 255. So this will extend the range of the image from 0 to 1 to 0 to 255. So image underscore display equals image underscore display dot cpu dot numpy dot as type np dot uint8. So now we have converted this image to unsigned integer 8. So as you recall that this image was converted to RGB, so we need to convert it back to BGR. So cv2 dot cvt color on image display, cv2 dot color underscore RGB to BGR. And now we have set of bounding boxes, masks and class and confidences. So we can use them to plot on our image. So let's write a for loop for 1 underscore mask b box cls conf in zip of pred underscore masks underscore np n b boxes pred underscore cls pred underscore conf. And if this confidence is less than opt.conf underscore thresh, we do not want to do anything and we just continue the loop. Otherwise, we define some random colors for each instance. So color equals a list of some random integers from 0 to 255, and we need it 3 times because color has 3 channels, R, G and B. So we are just going to copy this and paste here. And now image underscore display at 1 mask equals image underscore display at 1 mask into 0.5 plus np dot color d type equals np dot uint8 into 0.5. So this will paste the mask on the image. And now we need to define a label. So label equals, there would be 1 string input and 1 float input. So the names at integer of CLS, and then second one would be CONF. So now we need to calculate the font size and the text size. So TF equals maximum of opt dot thickness -1 or 1. So this means you cannot have thickness of 0 or below 0. And then T underscore size equals cv2 dot get text size from label 0, font scale equals opt dot thickness divided by 3, and thickness equals TF, and then index 0. Then C2 equals B box at 0 plus T underscore size at 0, then B box at 1 minus T underscore size at 1 minus 3. Now we need to plot this bounding box, but only if opt.noBbox flag is not set. So if not opt.noBbox, let's call cv2.rectangle on image_display, and the bounding box would be bbox at 0 to bbox at 1, and then second tuple would be bbox at 2 and bbox at 3. Then the color that we defined above, and thickness would be opt.thickness, and line type would be cv2.line_AA, which is anti-aliasing. Similarly, if opt.noLabel is not set, we want to put the label on the image as well. So let's do if not opt.noLabel, cv2.rectangle, image_display, bbox at 0, bbox at 1, then c2, then color, then -1, then cv2.line_AA. So this is going to fill the background of the label text. Now put the text with cv2.putText on image_display, label, then bbox at 0, bbox at 1 -2, then 0, then opt.thickness divided by 3, and it's going to be in white color, so 255, 255 and 255, and thickness equals tf, which we calculated above, and line type would be cv2.line_AA. And once all of these bounding boxes are plotted, we just want to return image_display, and if no bounding box was detected, we want to return the original image which we stored as image_. Alright, let's run this code, and there is an error. So I have typed this comma 2 times here, so let's remove this and run again, and I have made another mistake. Yeah, so model.pooler_scale, this should be a tuple, not a scalar, so let's add a comma here. And if we run the code again, it gives another error. So this should be cv2 and not cv. So let's correct this and run the code again. So yeah, this time we can see the output. So all the instances of person class are detected and plotted on the screen, all with different colors. Now let's test other arguments as well. So let's add -no_bbox. So this time bounding box is not shown on the instances. And let's also try -no_label. And now you can see that label is also not shown and only segmentation map is plotted. So now we need to define on video function as well. So let's define here below this on image function. So if webcam flag is set, we already know that the input is going to be a webcam. So cap equals cv2.video capture, integer opt.source, else cap equals cv2.video capture, opt.source. And let's see if the source is successfully opened. So if cap.is opened equals false, print error, that file cannot be opened, and return from the function. Otherwise success, image equals cap.read. Now we also need to determine the FPS of the source and width and height of the source. So FPS_source equals cap.get cv2.cap_prop_fps, and width equals integer of cap.get cv2.cap_prop_frame_width, and for the height same command is used, just change this to h for height and this width to height. And now we need to define a video writer. If opt.noSave flag is not set, then vid_writer equals cv2.videowriter on this save path, and encoding would be cv2.videowriter_4cc steric mp4v, and its FPS gonna be whatever we have detected above, so FPS_source, and its width and height would be whatever we have detected above, so w and h. Now we define start time equals 0. This is going to be used to calculate FPS. So while success, image equals cv2.cvt color and convert it to from BGR to RGB. Then image_display equals process frame, and we are going to pass this image. And if opt.showFPS is set, then we are going to calculate FPS. So current time equals time.time, FPS equals 1 over current time minus start time, and start time equals current time. And then we put this text on the frame. So cv2.put text on image underscore display FPS plus string of integer of FPS. Offset is going to be 20,7, and font is cv2.font underscore Hershey underscore plain with size 2 in color green 0 to 55 0, and thickness is 2. And if opt.view underscore img flag is set, we are going to show it in real time. So cv2.imshow in result window image underscore display. And if opt.noSave flag is not set, we are going to call vid underscore writer dot write and pass image underscore display so that it can be written in the video. Then we monitor key press, key equals cv2.wait key 1 and 0x ff. If key equals q, then break this loop, otherwise read next frame. And once all the frames are read and processed, just call cv2.destroy all windows. And finally, if opt.noSave flag is not set, we are also going to print where this video is saved. So print output saved at save underscore path. Now for video, same command would be used. Only difference is that now source is going to be ac underscore parkour.mp4. And here we have the result. We can experiment with all the arguments. Let's remove no vbox, no label, -view -img and -no save, and run this command again. You can see in the video output the color is not consistent with respect to each instance of person. That's because we are initializing color randomly for each instance here. So to get consistent colors, we can actually do video instance segmentation, which is a separate topic. Maybe I'll make a video in the future. And we can see this output is stored here, but it's not going to play because we have to make one more modification in the code. So as you can see in vid underscore writer, we have defined it with a specific width and height, but the image that we are storing has different resolution. So after processing this image, let's do image underscore display equals cv2.resize image display, and we are going to give same width and height here. So this time if we run this command again, we can see that the output is a lot bigger and it's stored in the hard drive as well. So now let me tell you how to run this on webcam. So Python segment.py -source 0, which is your webcam number, -, thickness. You can do 2 or 3 or 4 depending on the resolution of your webcam. Then -view -img, -no save, -no vbox, -no label, -show FPS. And now if you execute this, you would be able to see the results on the webcam in real time. So with that, I think I am done. If you have learned something of value today, leave a like and subscribe to the channel to watch more videos like this. Consider support on the Patreon to help the channel out. I will see you next time.